Okay, so the equation of a plane, that's the first thing we're going to tackle. And maybe I should add here the equation of a plane in 3D space. Okay, we're looking at three-dimensional space and we're asking what's the equation of a plane. So there are various ways to derive this thing. The way I'm going to do it is the following. So what determines a plane? Okay, how do I prescribe a given plane? Okay, what do I have to say about it? Is a vector enough to prescribe a plane? If I give you a vector, does it determine a plane? The answer is no. There are many planes that this vector is on, right? Do you agree? Okay. If I give you a point, does it determine a plane? Of course not. There are many, 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 many planes through a given point. Do you agree? So the claim is that if I give you a vector and a point, then it prescribes a specific plane. Okay? So remember, a vector, when I give you a vector, it can be anywhere, right? It's the same vector. This and this and this and this and this and this and this are all the same vector. They have the same direction and the same length. Do you agree? However, if I give you a vector and a point, it fixes a plane. Why? Not the plane the vector is on, but rather the plane the vector is perpendicular to. And I claim that that's unique. Okay? So let's think for a minute. Given a vector, there are many planes perpendicular to this vector. Okay? They're all parallel to each other. All these planes that I'm showing you here are all parallel to each other, and they're all perpendicular to this given vector. Do you see that? Do you agree? But if I fix a point, so I kind of root the vector and not allow it to be here, 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 or here, then there's only one. Do you agree? So given a point in a vector, there's a unique plane that goes through that point and perpendicular to that vector. Do you agree? So that's the geometric story. Now I want to somehow express it in a way that we can derive an equation. Okay, that's what we're going to do. So, given a point in 3D space, we're going to call it M naught, M0, and a vector, which we're going to call N, capital N. Usually we use lowercase letters for vectors, but here we're going to use an uppercase letter and a specific one, N, and it even has a name called the normal vector. That's what it's called. There is a unique, a well-defined plane perpendicular to N, and that includes or goes through or whatever M naught. That's the statement that we made so far. Now how do I find its equation? So here's the picture to go along with what we're doing. Here's a symbolic way of denoting a plane. The reason that it's symbolic is that planes are infinite, right? This is not a plane, this is just part of a plane. The plane goes in all directions infinitely. Do you agree? Just like a line is infinite. So this is symbolic. So here's the point M0. It's somewhere here. And N, the normal vector, I can draw anywhere I want, right? And the question is, what are all the points of the form x, y, z on this plane? What equation do they satisfy? That's what I want. Some equation that has x, y, z in it, such that any x, y, z on the plane satisfy that equation, and those are the only x, y, z's that satisfy that equation. That's the equation of a plane. Good? So I'm going to take a general point, any point on the plane. Here it is. Call it M. So M0 is going to be a specific point. X0, Y0, Z0. M is going to be any general point on the plane. X, Y, Z. And I'm going to draw the normal starting from M. Here's the normal, N. And the components of N are going to be A, B, and C. Again, this is kind of standard notation using A, B, and C. Okay. Now, I'm going to connect M0 and M with a vector. And this vector is going to be called M0M. That's this vector. Okay? And what do I know? That for any point M on the plane, if I start the normal at that point, then the vector connecting M0 and M is going to be perpendicular to the normal. Do you agree? This precisely captures those points on the plane. Do you agree? Okay, so M0M is perpendicular to N. Good? Okay. So let's see what these are. So what does it mean that M0M is perpendicular to N? I know how to say that. How do I say that? Right. The dot product should be 0. Do you agree? In fact, that's an if and only if statement. Right? Okay. And now I'm going to write this in terms of the vectors themselves. So this is if and only if. What is M? I want N to be first. Do you agree that this is the same as this? I could have wrote it like this right away. But we know that the dot product is commutative. So do you agree that this is the same thing? Say yes. Come on. Okay. So now, what is N? So N is ABC dot. What is M0M? How do I find a vector connecting 2 points? We did that. It's x minus x0, y minus y0, z minus z0. Those are the components. Do you agree? And this should equal 0. So what do we get? We get the equation of the plane. How do we dot component-wise? We just multiply each component with the appropriate one, with the corresponding one in the other vector. So we get a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. So a point xyz is going to be on this plane if and only if, when I connect it to M0 by a vector and take the normal starting at that point, they're going to be perpendicular. If it's not on the plane, they're not going to be perpendicular. Do you agree? So a point is on the plane if and only if it satisfies this, and this is if and only if it satisfies this. So this is called the equation of a plane. And for a given plane, A, B, C, x0, y0, and z0 are concrete numbers. They're specific. And xyz is a general point on the plane. We're going to see an example in a minute. Okay? So this is called the equation of a plane. Note that the equation has very explicitly, you can read off the equation, the normal, A, B, C. Do you agree? And you can read off the equation a specific point on that plane, x0, y0, z0. Okay? Another way of writing this, which still has the normal explicit in it, but somehow hides the other details. Remember that a, x0, b, y0, c, z0, those are all just numbers. x, y, z are the variables. So you can collect all the numbers. So you write ax plus by plus cz, and then all the rest of them, minus ax0, minus by0, minus cz0, you call d. Okay, it's a number. So that's an equivalent way of writing a plane. So another way of writing and both are used often, ax plus by plus cz plus d equals 0. Okay, so here you don't see the point x0, y0, z0 explicit. It's somehow hiding inside D. Okay, let's do an example. Let's see that this compiles, this makes sense. So, example. Let's find the equation. Let's find the plane through, so if I have 3 points in space, as long as they're not on the same line, they also determine a plane. Do you agree? If I have 3 points in space and they're not on the same line, they determine a plane. Does everybody see that? Okay. So let's find the plane through 3 points. 1, 2, 3, that's 1 point. 1, 1, 1, that's another point, and negative 1, 2, 0. So these are 3 points in space. Okay? So, I'm going to want to give them names. So let's call them, I'm really tempted to call them A, B, and C, but that would be very not wise, because A, B, and C are going to be the components of the normal vector, right? So I need to give them different names. So let's call them P, Q, and R. These are the 3 points. Okay. So how am I going to do this? First of all, what I'm going to say now is how we usually handle these sort of questions and these sort of challenges. First, we figure out geometrically what's going on, and then we try to spell it out. Okay? So what's going on here? We have 3 points. How do I get the equation of a plane? Well, how do I know the equation of a plane? How did I prescribe it? I need a normal vector and a point, right? So a point I even have 3 of them. That's a non-issue here, right? What I need is to somehow get the normal vector out of these 3 points. Okay? So I have 3 points. How do I get the normal vector? Answer. And this is kind of the creative part in doing these things. 2 of the points you can connect with a vector. Here it is. Then one of the points and the third one you can also connect with a vector. So the 3 points give you 2 vectors on the plane. Do you agree? Now, take their cross product. You get a normal. Do you see that? That's what I'm going to do. Let's do it. So, PQ, the vector connecting P and Q, is just subtract the coordinate. So it's 0, minus 1, minus 2. 1 minus 1, 0. 1 minus 2, negative 1. 1 minus 3, negative 2. That's how we get a vector connecting 2 given points. Remember? Okay, that's PQ. PR, so I chose P to connect to the other 2, is minus 2, 0, minus 3. Do you agree? Note that I'm not letting the fact that points are written as triples in parentheses and vectors are written as triples in parentheses, I'm not letting this confuse me. This is just shorthand notation for 0I minus 1j minus 2k. Okay, good? Okay, and now I need the normal. So the normal is going to be PQ. I have to choose which one I take first. So I took PR here, cross PQ. It doesn't matter. Okay? This is going to be a vector which is perpendicular to the plane on which these 3 points lie. Does everybody see that? Can you all picture that? Okay? And note that it's not unique in any way. If I take a vector that's 3 times that, it's also going to be a normal. Okay? The equation is not unique. Okay? Just like the equation of a line in 2 dimensions is not unique. Okay? You can write y equals 3x plus 4, or you can write 2y equals 6x plus 8. That's the same line, right? And that's what's going to happen if you multiply the normal. You're going to multiply the equation by some fixed constant. Okay, so the normal is not unique, nor is the equation. So how do I do this? I know how to do this. It's this determinant business, remember? So it's I, J, K, and then the component. So PR was minus 2, 0, minus 3, and PQ was 0, minus 1, minus 2. Do you agree? And now let's do this. So what do I get? Let's see. In the I direction, look up here. See that you agree and you know what you're doing. So in the I direction, it's 0 times negative 2, 0, minus 3 times minus 1. Minus 3 times minus 1 is 3, but it's in a minus because of the this minus this. So it's minus 3. That's the I component. Good? What's the J component? First of all, there's a minus because the J comes with a minus. Plus, minus, plus. And now I need minus 2 times minus 2, 4, minus 3 times 0, which is 0. So I get that 4, but the minus is because of the J. And then the K component is minus 2 times minus 1, 2, minus 0 times 0. Did everybody follow? So you know determinants now. Good? Okay, you're all determinant experts. Okay, so what is this? What did I just find here? I found the normal. Okay, this is A, B, and C. This is the normal. N is this. A is this, B is this, C is this. Good? So what is the equation of the plane? I need to choose a point, doesn't matter which one. Again, I'm going to get equations that look different if I take different points, but they're the same equation. They prescribe the same plane. So let's choose P, for example. So P is going to be now x0, y0, z0. That's the m0, the point, the chosen point. This is the normal. The equation of the plane is going to be A, x minus x0, plus B, y minus y0, etc. Okay, so the equation of the plane is A minus 3 times x minus 1 plus B minus 4 times y minus 2, y0, plus C plus 2 times z minus z0, z minus 3 equals 0. That's this plane. You can verify, for example, that the point R minus 1, 2, 0 lies on this plane. Let's do it quickly. Minus 1, so I get here minus 1, that's minus 2 times minus 3. I get 6 here. 2, this dies, and 0. 2 times minus 3, I get minus 6. 6 minus 6 equals 0. The point R lies on this plane. Good? Clear, everybody? Okay, another way of writing this same thing. So this is the way of writing it with the x0, the y0, and the z0. Another way of writing the same thing, minus 3x minus 4y plus 2z, And then there's going to be a number. What's that number? It's minus 3 minus 1, that's 3, plus 8, that's 11, minus 6, plus 5. This is with the D. The other way of writing it. Clear? So that's how we give an equation of a plane in three-dimensional space. Questions? Everybody good? Okay, to be continued next time.